Our second lesson of the second half of our first unit is going to be split into two parts as well. And so our first focus is to kind of deal with these conditional statements. And so we're going to learn a little bit about what those are. Our objective is to make sure that you'll be able to write conditional statements based on their truth values, find their truth values, and along the way we will write biconditional statements, we'll write the inverses, the converses, the contrapositives, etc. So there's a lot of vocabulary to learn here. There will be a lot of writing to do. So this may be a bit burdensome in that we're not going to be doing a whole lot of normal calculator type math today, but we will be doing thinking, and we'll be thinking about our writing, all right? And so that might be a little bit of a challenge for us. So a conditional statement is basically an if-then statement, all right? An if-then statement. If I show up late to school, then I will be marked tardy, right? That's just an if-then statement. You shouldn't be, if you don't show up late to school, then you will not be marked tardy, all right? And we're going to have a name for those kind of statements. Each conditional has two parts. The hypothesis is the statement that comes after the word if, whereas the conclusion is the statement or the part of the sentence that comes after the word then. It's important to just separate those ideas from the word if and from the word then. So the hypothesis does not include if, and the conclusion does not include then. And part of the reason why we do that is so that we can flop those sentences around a little bit, flip them around and kind of think of them in different lights, all right? So the way that we typically notate this is P arrow Q, which means if P, then Q. All right, so it's sort of a weird notation that sort of simplifies our writing and simplifies our thinking a little bit. But it also helps us think about how we might flip those statements around. If Q, then P. If not P, then not Q. Or if not P, then is Q true? And so we kind of think through these logical statements. Writing them and thinking them is part of it, but then thinking about the veracity of those statements, the truthfulness of those statements, is the next level, all right? And so we're going to wrestle with just the beginning part of this lesson. Part of this will be pretty straightforward, pretty easy. Some of this might be challenging, especially if you have reading difficulties or writing difficulties. Please advocate for yourself, ask me questions, or just make sure that we can navigate that well together. Because we still want to make sure that if the reading or the writing is the challenge, that we can still do the thinking part. The thinking part should be appropriately challenging for everybody, all right? Just like you have to think in your English class to make a thesis statement and then to back up your thesis statement in your conversations or in your essays, the same thing will be true this semester in geometry. So here is a mathematical statement, a geometry statement. If two lines are parallel, then they are coplanar, all right? The hypothesis here would be the part that comes after if. Two lines are parallel. The conclusion would be the part that comes after then, the lines are coplanar. And so identifying hypothesis, identifying conclusion is kind of that first iteration of understanding what a conditional statement is. All right, we're on the way to being able to write these conditional statements. So identify those two pieces in your notes. All right, you can register to vote if you are at least 18 years old. Now this sentence is a little funny in the way that it's arranged. It's not arranged with the if statement first, but we do have a hypothesis, a phrase that comes after the word if. So after the word if, you are at least 18 years old. There's not the word then, but we realize that there is some result, some conclusion. If this is true, then you can register to vote. All right, so sometimes the sentence structure, based on the way that the English language works, we might have things organized slightly different. All right, so we want to be attentive to that, we want to be aware of that, and be flexible with how our English language works. You may have a statement that is not written as an if-then, but then we will be tasked with thinking about how to write it as an if-then statement. An acute angle measures less than 90 degrees. This is a fact, this is a true statement. How can we write that as an if-then? There's maybe multiple ways, based on the way that the English language works again, in which we can make an if-then statement from this sentence. So one way to write that would be if an angle is acute, then its measure is less than 90 degrees. You could also write that as if an angle measures less than 90 degrees, then it is acute, all right? When a conditional can be written forwards and backwards, we'll have a special name for that. So I want you to be thinking about Are there multiple ways to write that and still have a true statement? All right. Sometimes you can flip the sentence around and it becomes not true. All right. So we want to consider that as well. A parallelogram has two sets of opposite congruent sides. Again, a geometric concept, not a high school geometry concept. This is something that you would learn in the elementary grades. But can we write that as an if-then statement? Pause the video and see if you can do that. See if you can write that as an if-then statement. Pause the video. Here, you'll notice that the way that I structured the sentence maybe is a little clumsy, maybe a little cumbersome in how we maybe have to insert a word in order to make a sentence that makes sense. If a shape, if a quadrilateral, if it, you don't want to say it, you don't want to use that pronoun in the beginning of the sentence, right? And it can come in the end of the sentence, right? And it can come at the end, but if we're talking about an angle, then we want to put angle, not if it is acute, right? We want to talk about an angle, but then its measure, the pronoun can come later. We can't say if it is a parallelogram, then it has two sets of opposite congruent sides, because that might not be a great definition, right? Or it might not be a true statement. But if a quadrilateral is a parallelogram, then it has two sets of opposite congruent sides. So here, sometimes we have to be flexible with the language component. And that might be challenging for you if you struggle with language, or on the other side of it, if you struggle with the content, like if you don't know what a parallelogram is, then maybe it's hard for you to write that sentence. Right? Be aware of that. What is the struggle? Where's your challenge? All right? And if you're aware of that, then we can address it. Truth value. Truth value is basically a 1 or a 0. Either it's true or it's false. And you can have conditional statements like, if the sky is blue, then it is raining. All right, that is a conditional statement. It's not necessarily true, right? Maybe it does rain when the sky is blue. Maybe the sky is blue regardless of whether or not it's raining, right? And so we have these truth values that we can ascribe to these conditional statements. It's just like when we would have a conjecture in the last lesson, but we could show that it's true, or we could provide a counterexample to show that it's false. So likewise, if we're going to show that something's true, we have to prove that every time the hypothesis works, then the conclusion happens, right? If hypothesis, then conclusion always. This is really hard to do. And that's really the crux of this semester together. We're going to be doing geometric proof, where we're going to show if this is the case, then I know that this will always be true, this conclusion. But to show that a conditional is false, all that we need to do is have the hypothesis true, but a different result, a different conclusion that is not the conclusion that is either given or conjectured, right? So we can prove that that's false, again, by using a counterexample. Notice how I say one counterexample. You will do yourself no favors by listing, well, it could be this, or it could be that, or it could be that. Don't list a litany of different things that would be counterexamples, just provide one. It's kind of nice to be able to say one thing and render the whole conditional statement false, all right? There's power in that, all right? Just giving one counterexample instead of 30. All right? But give an actual counterexample. Don't just say, well, we could be talking about all these other things. Well, don't list those other things. Be specific. Give a counterexample. These truth tables, I'm not going to explore with these too much, but this is a great way to outline your thinking if you're trying to determine if our statements work. All right? So if the hypothesis is true and the conclusion is true, then that means the conditional statement is true. If the hypothesis is true, but you get a different conclusion, the conclusion is false, that means the conditional statement is false. If the hypothesis is false and then the conclusion is true, that means that our conditional is true. All right? It's kind of a weird situation. If the hypothesis is false and the conclusion is false, that means that our conditional is true. Go ahead and fill that truth table out. It kind of considers all possibilities for P and Q. All right? Find a counterexample to show that this conditional is false. So this statement might be true for some values of x, but we're going to find basically a value of x that shows that this statement doesn't work for all values of x. So we're going to write down this algebraic statement. If x squared is greater than or equal to 0, then that means x is greater than or equal to 0. So to find a counterexample there, I'm going to use a negative number. All right? I'm going to use any negative number. My counterexample isn't any negative number. I'm giving a specific negative number. I'm using -1. You could use -5, or you could use -2, but we're giving an actual counterexample. Negative 1 squared is greater than 0. Negative 1 times negative 1 is positive 1, which is greater than 0. But negative 1 is less than 0. It is not greater than or equal to. So here our hypothesis is true in our counterexample, but our conclusion is not greater than or equal to 0, right? It's something different. And so you want to make sure that you think through it in that way. Now you could give another or various counterexamples, but if it asks for a counterexample, you need to give one. Don't just use generalities and say, oh, you could use any negative number, because you're not actually providing a counterexample. You are arguing and you are using logic, and that's awesome. You're not wrong, but you're not providing a counterexample when you do that. So if you're asked to give a counterexample, or if you're tasked with providing a counterexample, then actually provide one. All right, converse. This is kind of interesting. This is where we take a conditional statement, if P then Q, and we flip-flop the P's and the Q's so that we have if conclusion, then hypothesis. So we're just doing a swap here. The issue for many students when you're first doing this is paying attention to English language grammar conventions. Again, if English language is an issue for you, if those grammar conventions are hard for you, let's have that conversation so that I don't hold you to an account that's higher than your current language abilities, right? We want to make sure that we're taking care of each other. Sometimes you write a converse, and it's true. Sometimes you'll flip the statement and you will create a false conditional. Sometimes your job is just to write it. Write the converse, all right? Even if it's wrong. Then we can assess the truth value. Then we can think about counterexamples, etc. So, here we have this statement. If two lines are parallel, then they are coplanar. If I flip that statement around, I say if two lines, again, we put the noun form here, and we put the pronoun form in the end, all right? The noun form of our subject, the pronoun form of our subject at the end, all right? So it's not a hard swap. We don't say if they are coplanar, then two lines are parallel, right? That sentence doesn't flow in the English language. So if two lines are coplanar, then they are parallel. So what we did here is we wrote just the converse. Now this statement is not true. If two lines are in the same plane, that doesn't make them parallel, all right? But if two lines are parallel, then they have to be in the same plane. That's the definition of parallel lines. All right, finding the truth value of a converse. So we just kind of talked about that with the last one. If a equals 5, then a squared is 25. This is a true statement, all right? The converse, if I flip that around, then, as I'm using a conditional, if a squared equals 25, then a equals 5. All right, this statement is not true because I can provide a counterexample that says I have a value of a that when I square it I get 25, but it's not equal to 5. And you might be like, wait, what? So let's think about the conditional. This conditional statement is true. A, when I square it, when I take 5 and I square it, I do get 25. All right? So this is true. The conditional statement is true. But the converse is false. If I'm going to say that it's false, I have to provide a counterexample. All right, so here is a value, -5. If hypothesis is still true, then conclusion, different conclusion. So -5 squared equals 25. -5 times -5 is positive 25. So I have a value for which the hypothesis works, the former conclusion, but now our new hypothesis in our converse. But our conclusion is different than what we started with. All right, that's providing a counterexample. All right, that's the end of our first half of lesson 5. All right, so hold tight with that, and we'll get on to part 2 later.